Hello everyone, welcome to the lecture on decision tree learning from egate.ai. I am Dr. Amrith Krishna, and today we will continue with the second part of the decision trees lectures, and we will look into how exactly a decision tree is learned. So let's start our class. Learning decision trees. So let me bring in another example or an illustration of how exactly the learning happens using an example. So if you remember, we had an example for naive Bayes where we were asking the question that given the conditions, the weather conditions of a day or weather conditions of a given day, whether we should play tennis or not. So let's revisit the will I play tennis or will we play tennis today example. So this time, but we will use it to build a decision tree. So the problem setting is as follows. Imagine that we need to decide whether to play tennis or not for a given day. Let's do that using decision trees. So we are considering 4 features all about the weather. The features are outlook with 3 values: sun, overcast, rain; temperature with hot, mild, cold; humidity with high, normal, low; wind with strong and weak. And it is a binary classification task. It either has a yes or a no answer. So there are 2 features with 3 possible values, and I think there are 3 features with 2 possible values and 1 with 2 possible values. So this is our feature space, this is our label space. Now let's get into how the learning happens. So let's say we have collected data from the weather patterns of previous 2 weeks, which you can see here. There are 14 data points or 14 rows, implying we have collected it for the past 14 days. And it does not suffice. These are just the features. We also need to have the labels, that is our decisions for those past 14 days. Labels, features. This is what we have collected. So this is a good time to discuss probably something called as batch processing versus online processing. So decision tree assumes that the data comes in a batch prior to the learning. So we have access to some data or a batch of data prior to the learning process can begin. This is an assumption we have for a learning algorithm like decision tree. So we call them as batch learning algorithms. An alternative here is the online learning algorithm, where so batch learning we already know. It is data is processed in a batch, one instance at a time. It can happen then and then. So this is a batch learning algorithm, and the learner recursively builds a decision tree top to down. So it is a top-down recursively built structure which is built using a batch of data which is available a priori. And during the learning, there are only 2 decisions that the learner has to make. So 2 decisions for learner to make. And what are these two decisions. One is that what is the most important feature. So let's say for the time being, we somehow magically decided that Outlook is the most important feature. So one decision is that at any point, which is the next best feature, right? Best feature. Now, since we know that, or since we are assuming that somehow we have got Outlook, maybe an oracle told us for the time being, we are assuming that Outlook is the best feature. Now, from our understanding of data, we know the possible values that Outlook can take. It can take three different values: sunny, overcast, and rainy. So the learner needs to now decide an action for each different values of the feature. So there are two decisions, right? One is the best feature, action for feature values. I think I will not clutter it here. So I will just say action for every value of the feature. That is the second decision to make. And now with these two decision points, we keep on building the tree, or the tree keeps on growing top down based on the decisions. So this is roughly how a decision tree algorithm is approached, or a decision tree algorithm goes on to build the tree. And in fact, what we have discussed so far is essentially the idea of the ID3 algorithm. It's one of the earliest, or probably the first algorithm that tries to build a decision tree. So let's dive deep into it. So ID3 algorithm takes in a data set. Yes, for legacy reasons, I am using the notation as it is used originally. So ID3 algorithm takes in S, which is the data set, and a set of features, right? So here is the data set and a set of features where every feature has a value for each of the data point in the data set. And generally we assume that the features are decided in such a manner that those are relevant to the task at hand. So with this input, we start the algorithm. Now let's do a walk down of the algorithm. So first, let's take a base case in the recursive case, or let's take a trivial case here, right? So this is the base case in the recursive approach. So that's very trivial here. If all the examples have the same label, let us assume there is a data set, and every example in the data set have the same label. Now it may mean that the data set is not a well represented data set. That is one possibility, or possibly the data set is well represented and in reality we only have one label. These are the two possibilities, but that distinction is not important here. All that the algorithm can do, that if it is provided with all the examples that have the same label, then it just needs to return a single node tree with the label. So its root node, or the single node that it has, will be that label and nothing else. So there is no feature that needs to be decide the label of the input, because all the inputs, all the examples have the exact same label. So now life isn't always that straightforward, unfortunately. So most of the time we will spend on the rest of the logic, which is the otherwise case, which is more realistic. So here we are assuming there are more than one label for the for the data set, that is for all the data points given to us. So so here what we are doing, we are first of all creating a root node for the tree. Let me do it properly. Yeah, create a root node for the tree. Here we need to decide which one of the features need to be a root node. So let us say we have n, say 20 or 30 features. From those 30 features, I have to select the best one, and we have to assign it to the variable a. So let's say, using some heuristic, which we will define later, currently we will say that we will select the best attribute from the attribute set that best classifies as, and we assign it to a. Now for each possible discrete value v that a can take, now we are entering a loop. For each possible value v that a can take, we create a new branch. So we have previously seen that we start off with an attribute, then for every value that that attribute takes or feature takes, we create a branch, and that's precisely what is written in step 1. Add a new tree branch for attribute a taking value v. So we are in the loop, so we are iterating through each value, and we are assuming there is a discrete value for this. And let's say that SV is the subset of examples in S with A equal to V. So it is guaranteed that every input will have that feature, but only a subset of the examples will have a particular value for that feature. And that is what SV is representing, where the A is equal to V. Now if SV is empty, which is very much possible, like the green triangle example that we saw in the previous lecture, add leaf node with the common value of label in S. Now this is very interesting. So first of all, we started off with a loop where we are saying that we are considering every possible value for the attribute, every possible discrete value for the attribute. Let us say there are only 3 values. Then we create 3 separate branches, or the loop will iterate for 3 times, implying that we will create 3 separate branches. So now we said that we look for only those examples where that particular value of the attribute is there for an input, or we take that subset of the data set. And if it is empty, we assign a default value. Now, roughly speaking, why the most common value or the most common value of the label in S is assigned? It's pretty straightforward. It's an intuitive thing to think about it. Statistically, the most common label will be the most likely, or probabilistically the most common label will be the most likely, and we are simply going with the most common label. That's it. There isn't a lot of complexity there. It's as simple as that. Now if that is not the case, if there is a finite or there is a valid subset, a non-empty subset of the data set that has the attribute value v, then we make a recursive call. So it's the ID3 algorithm. So we make a recursive call to the same ID3 algorithm, but this time which means that we have to create one more node and have to branch out. So we are giving in all the input as the previous case, except the attribute that is being currently chosen. So until no attribute remains for a recursive call, the recursion can continue. And this summarizes, or this largely explains, the decision tree algorithm or the ID3 algorithm. By the way, there are many different decision tree algorithms. So I must specifically say this slide describes the ID3 algorithm, and it is a recursive greedy first algorithm, greedy heuristic based algorithm. Now, if you look at the algorithm, most of it is concretely defined. There isn't a lot of confusion, except for step 2. In step 2, we talk about the best attribute. So how do we select the best attribute? So please understand that even though we talk about root, since it's a recursive call, there is a root selection at every recursive call. So we are basically talking about at every node creation, we need to make this decision. So here our definition of best is rather unclear or ambiguous, and we have not mentioned how exactly we will find the best. So in other words, we need to know what does it mean for a particular feature to be best, or more generally, what kind of trees are preferable or what kind of trees are better. Sorry. Now there are many ways to define the best, and often a lot of them can be thought of as valid ones. It's not that there is only one clear way to define best. So let's see that for starters, let's say that the way ID3 algorithm decides about it is that it prefers smaller trees over larger ones. So when I say smaller trees, trees with lower heights. So ID3 algorithm prefers ID3. So in a different algorithm, it can be different. So that's why I said there are multiple valid ways to think about how to think about being the best node selection approach. But ID3 prefers smaller trees. And what is small here? That is tree with lower heights. Let me write that properly. Lower heights. So the intuition behind this preference is the Occam's razor, where simplicity is given precedence. So why is it this philosophy of Occam's razor, which is so general, and why is it sensible for the creators of ID3 to choose it? So let's take an extreme case. We have a data set where an input is represented with thousands of features. However, let's say when we build our decision tree, we find that just one feature, or maybe a combination of two features, can perfectly assign labels. Now, either of the cases mean ridiculously small trees, right? You either have one node or you just have a tree of height 2 because you have two nodes. And irrespective of how small they are, if we have a small tree and it can perfectly do the classification, then how likely that is by accident? Now, on the contrary, on the flip side, if we have a really large tree, say of height that covers all the tons of features that we have, then it is more likely to be an accident, as with such a large tree, we may fit any reasonable data set, and it can be like suspected for, or it can be thought of as a case of overfitting. It may even fit the noise in the data with such a large tree. So that's the intuition this heuristic is trying to capture, that smaller is better, or smaller trees can fit better. Or Occam's razor in general says if a phenomenon can be explained by two models, then choose the simpler one in a very simple manner. Second thing is that the greedy, so that's with the first one. Then this algorithm is a recursive algorithm. It is a greedy heuristic search for a simple tree, but cannot guarantee optimality. Now, why do we settle with something which is just a greedy heuristic, which does not guarantee optimality? The answer to that is that we have said that we are going for Occam's razor. Based on that, we have a bias, or we prefer smaller trees over larger trees. But finding the minimal decision tree consistent with the data is an NP-hard problem in itself. That's why we go with a greedy heuristic approach that cannot guarantee optimality. The main decision in the algorithm is the selection of the next attribute to split on. So now the most popular heuristic is information gain, which originated with the ID3 system or the ID3 algorithm of Quinlan. They first proposed this algorithm. So I believe you might have encountered this term entropy in information theory or associated topics. And entropy, from the information theoretics perspective, can be thought of as impurity or disorder of a set of examples S with respect to, let's say, a binary classification task. It is simply defined as the minus p positive log to the base 2p positive minus p negative log to the base 2 p negative. So this is specifically for a binary classification task that I'm talking about. There are two labels, the positive and negative label. And here p plus and p minus are the proportion of the positive and negative examples respectively. So it can be generalized to k possible values as follows. So in general, for a discrete probability distribution with k possible values with probability p1 to pk, the entropy is given as the summation of pi log to the base 2 pi for all the k discrete variables. So if all the examples belong to the same category, then the entropy is 0. So there is no disorder, right? Everything belongs to the same category. That's one extreme. And if the proportion of positive and negative examples in a binary classification is, say, equal, that is half, right? Then the entropy is 1, because that's perfect disorder. So 0 means no disorder or no impurity, and 1 means as impure as it gets. So if we go back to ID3, our intuition is to choose the attribute that reduces the label entropy the most. And ID3 operationalizes it via information gain. So ID3 operationalizes this attribute selection, which is via reducing the entropy, using information gain. So the information gain of an attribute A is the expected reduction in entropy caused by partitioning on this attribute. So the gain for an attribute A for a given data set S is that it is the entropy of S minus summation of SV by S, where SV is the subset of those data points that has a particular value for the attribute A, that has a particular value V for the attribute A. So it's SV by S times entropy of SV, and we are doing the summation of all such values. So entropy of partitioning the data is calculated by weighing the entropy of each partition by its size related to the original set. Partitions of low entropy lead to high gain. So summarily, high entropy implies high level of uncertainty and low entropy implies low level of uncertainty. The hypothesis space that ID3 searches over is the space of all possible decision trees, which translates to all possible Boolean or all possible discrete functions. It is a greedy algorithm and it never revisits its decisions. So if we have to find the best tree, we need a tractable solution such as hill climbing without backtracking, because it's an NP-hard problem to find minimal decision tree consistent with a set of data. And since we are using this greedy heuristic, we are doing something like a hill climbing without backtracking makes sense. And we make the statistical decision using all the data available to us. So this concludes our lectures on decision trees. So to summarize, the representation, yes, what are decision trees? These are hierarchical data structures that represent data. Now about learning decision trees, the answer we encountered was to use the greedy heuristic called as ID3. There are many ways to learn decision trees. For instance, CART is another, and C 4.5. So decision trees are so classical that you will find at least hundreds of different variants for it. I am not going to get into it, but yeah, just for the sake of exposing you to some diversity, I was just mentioning that there is something called as CART and C 4.5. In ID3, we simply find the most informative attribute and branch out for different values of that attribute. We keep on recursing on the splits or branches. And that's summarily defined as ID3 as a learner for decision trees. Thanks for attending this lecture. We will now attend the next lecture, which is still on the classifier series. So we will look into perceptron, neural networks or multi-layer perceptrons. We will look into nearest neighbors. We will also look into what is called as I think SVM, support vector machines. Perceptrons. Yeah. Thanks everyone. See you in the next lecture.